So the work I'm going to present today is about zero-size heap allocations. So, since 10 years or so, we have lots of software vulnerabilities due to heap overflows and everything. So zero-size heap allocations are one instance of potential heap overflow. How many of you guys do C programming? Good. So this talk is rather technical, so if I'm too fast or maybe too slow, just let me know because I want everyone to get it. And there are going to be lots of examples, so hopefully it's going to be all clear for everyone. So even though most of this work has been done on Microsoft code bases, so mostly we're going to present examples on the Windows kernel. This is not a Windows-specific problem. This is present on Unix operating systems as well, on mobile code as well. So in this CCC, we've had lots of talks about infrastructure attacks and everything. And by the way, thanks for the great event because it was really interesting to attend all those talks on GSM and stuff. And we're going to be at slightly at the highest level here, since we're not going to touch to the infrastructure, but see what happened at the application level. So we're going to see the kernel stuff, we're going to see a couple of application stuff, and keep in mind that it absolutely applies on mobile, not only Windows Mobile, but also whatever mobile operating system you wish. So let's get started. So what is a zero allocation? Obviously, you know that you have dynamic memory allocators on all desktop operating systems. So whenever you need to allocate memory dynamically, you call a function malloc. So malloc takes a parameter that is the size of the memory you want to allocate. The thing is, when you put a size of 0, the behavior is implementation defined. So it's not specified by the ISO C99 if you either need to return a null pointer or if you need to return a valid pointer, etc. So it's basically up to the implementation. So as we will see, most of the time when you do a zero-size heap allocation, the malloc function and also many other functions that allocates memory dynamically, they return a valid pointer that is pointing on a valid heap chunk. So for example here, we allocate 0 bytes, the pointer is not null, so the check is not sufficient. And if you have a side condition, say an integer underflow or overflow, in that case the underflow size -1, then you have a buffer overflow, and checking the pointer for null is not going to save you from anything here. Second example, you have an arithmetic operation, say a multiplication or even an addition. The thing is, the result can still be 0. Say in that example, data arrow NBR is 0, multiplication gives 0, so the size stays 0. You allocate 0, you test for the pointer null again, but no error is reported. And then you dereference the allocated pointer to an invalid location. So in that case, you're going to try to write to an invalid location, PTR arrow field. Third example. So here you read the size from an untrusted location and you add the size of a structure, say the size of a header, for example. You allocate, and then you check for null again. And here, so it's a pretty obvious flow again, but can you understand why this is potentially buggy? It's basic, right? Well, if you have an integer overflow, then you can have a size that is small and then potentially 0, potentially small, maybe 1, maybe 2, you don't know, it depends on the size of type and depends on the untrusted value as well. And here you trigger again a heap overflow. So this third scenario is not specific to zero allocation. I mean, it could be the classic, this is a known case of integer wrap and allocation, so it has been discussed a lot before. However, our characterization of zero allocation also handles this case, so it's a generalization of the integer wrap case. So any questions so far? I know we just started, but maybe we want to discuss things. Okay. All right. So yeah, zero allocations, in my opinion, are not a new kind of vulnerability. Those are more a new kind of technique to find a specific class of heap overflows. So because buffer overflows in the general case are very hard to get rid of, we want to restrict the attack surface to something that is tractable, that is only the cases where the size could potentially be zero. So even big code bases, this is potentially a small number. I'll give you some numbers later so that you can realize exactly. And also in Microsoft, we do lots of analysis. So we do lots of static analysis, we do lots of fuzz testing, we do lots of code review. So we have a small internal tool that is based on a theorem prover that allows us to uncover all those locations in the Windows kernel and actually any code base. So that allows us to filter out the code review we have to do, since we have to review many millions lines of code. This is very practical to actually be able to give a higher insurance of the absence of such particular bugs. Something I should say is that our tool works mostly for C programs, so we do that from the source code. It's possible to do that at the binary level too. However, since we have the source code, we just don't bother, basically, and it doesn't make sense when you're in Microsoft to do binary analysis, so we do everything on the source code. The support for C++ is a work in progress, so we start to target C++ programs as well, such as browsers and stuff, but it is going to be for later, not for this talk. Okay, so a little outline of the presentation. So first of all, I'm going to run a couple of tests so that you can see what is the actual result of zero-site heap allocations on a couple of kernel functions of the Windows kernel. And then I'm going to introduce 3 different techniques for detection. So all I'm going to talk about is static analysis. So we had a couple of talks on dynamic analysis, how to detect this in runtime and everything. This is not what we're going to talk about. So all the detection that happens here is done without execution. It's done only by compiler plugin. So at the build time, we are able to detect all those instances of potential zero allocations and where a memory corruption can happen. So the tool is called Havoc. So it's developed at Microsoft Research Redmond in the research in software engineering team. It's a team of Thomas Ball, who had a couple of success in the last 10 years with automated tools such as SLAM, the SLAM model checker. It has been very successful on small scale. So when I say small scale, it's about drivers of up to 20, 30,000 lines of code. Here, we don't use model checking as in SLAM. We're going to present a technique based on theorem proving. I'm going to give a couple of examples of this later. And as the last part, I'm going to generalize the property of zero allocation. So sometimes you don't have a zero allocation, sometimes you have a near zero allocation. So if the size holding variable can be desynchronized compared to the size of the allocated memory, even though you don't allocate 0 byte, you can still have a couple of problems. And I'm going to give one example of bug we haven't covered. Okay, so is your environment exposed? Let's see on Windows. For the Windows kernel, we have a function in the Windows kernel called xallocate pool with tag. So xallocate pool has a couple of associated API. Basically, the first parameter of xallocate pool with tag is a size, and just ignore the 2 others. But when you call xallocate pool with a 0 size, it actually returns a valid pointer, as you can see on the right side. This is just a dummy kernel driver I wrote. In fact, if you look at the code, at the binary code for this function, you can see that whenever the number of bytes you have to allocate is 0, you actually put the size to be allocated to 1. So when you do a 0 allocation, you have every time, most of the time, you have a couple of bytes that are allocated. So for the case of the Windows kernel, this is 16 bytes, because you can see that if the EDI register is 0, then it's incremented, and then it's rounded up. So rounded up plus 15, which makes 16. So it means that if you do zero allocation, sometimes it's not a bug. Sometimes nothing happens. If you don't touch the pointer, nothing happens. If you touch the memory below 16 bytes, nothing happens. However, if you dereference the field of a structure that is beyond the 16 bytes offset, then this is where you start to have memory corruption. Couple of tests for userland. So on Windows, you have mostly 3 userland functions to allocate memory: malloc, heap alloc, and virtual alloc. So virtual alloc is the most low-level function that is called by malloc and heap alloc. And malloc is used for C programs, while heap alloc is used for C++ programs mostly. So same thing, you can see here that the return for malloc and heap alloc with a 0 size is not null. So it actually returns a valid pointer. However, virtual alloc, which is very rarely used directly, returns null. So the risk you have if you just use virtual alloc is to have a null dereference, but it's not very interesting in userland. Other operating systems, for Linux, same behavior. Linux with PAX, same behavior, except for kernel land. So PAX introduced a very nice mitigation for zero-size heap allocations in kernel. Basically, by default, the kmalloc function on the Linux kernel returns 0x10. So it's vulnerable to null pointer dereference kind of attack when you map the null page and everything. So it's not a very good idea to return 0x10 by default, because you can still have a dangling pointer. When you have the PAX patch that is part of grsec, they change this value to FFFFF000, which is the address of the first byte of the last page of the address space. So whenever you touch this pointer, and I should say that this page is unmapped. So whenever you touch this pointer, you just touch unmapped memory, and so nothing can really happen. You just crash the kernel, you cannot exploit anything. For other operating systems, all of them are also exposed. On FreeBSD userland, the malloc function, when you call it with a 0 size, return a constant that is 0x800. So don't ask me why exactly they return 0x800, because it doesn't seem to be any specific value. Maybe someone knows? A FreeBSD developer in here? No? Okay. Anyway, this makes zero allocation in userland and FreeBSD unexploitable. Because, well, unless, of course, you know how to exploit null pointer dereference in userland, which I don't know, since null pointer dereferences are mostly exploitable in kernel. Yes? Are you talking about userland or kernel here?
It's on, but okay, jetzt it's working. Okay, so I'm thinking about PC architecture in general, because there are some magic numbers in the old PC architecture, because there were some dirty hacks in earlier time that were always used until today, because everything has to be compatible to the old or original PC. And so maybe this number you have to find in Etherbox or somewhere, maybe it has something to do with the MMU, that it will block memory or something.
I don't know. As I said, I don't know exactly the reason for this number. If you look at the runtime dynamic linker or something, or like maybe the allocator for FreeBSD userland, maybe you can get the reason without too many effort, too much effort. However, it's a detail. We can talk about it later. On other operating systems, Solaris. Solaris is kind of interesting because you have multiple API to call to do a dynamic memory allocation in the Solaris kernel, but there are APIs in Solaris kernel. When you call them with a size 0, it actually returns null. And in the Solaris kernels, many times you will actually, yes?
Isn't this because the Solaris kernel introduced a whole new thing about allocating memory as allocating integer ranges? and had this whole object-oriented way of handling those ranges?
I don't think it's related to this because it's not specific to Solaris 10. So we just tested on Solaris 10, but many versions of Solaris actually have the same behavior.
So it's not a VMEM. It's not a VMEM feature. It was previous in the. It was previous as well.
Yeah. It's not specific to 10.
Thanks.
So what I was going to point out is that many times when you do a dynamic memory allocation in the Solaris kernel, you're not expected to fail. So it happened that the Solaris kernel fails to actually check the return value of dynamic memory allocator functions. So if when you return null on the size 0, it's kind of a problem. Anyway. Any more questions about that? So while I'm at there, I must say that I did most of the job I did all the job on all the Microsoft code bases, and many people actually assisted me for the Unix job. So Damien is here. Enrico Perle actually assisted me on the Solaris work, and also thanks to the PAX team, with whom I've done a couple of tests for Linux. Okay, so let's give a couple of examples now that we have done all the taxonomy and everything. This is an example from the Windows kernel, so it's a true example that was fixed. Imagine you have a system call. So in that case, I called my syscall entry point. It takes two parameters. One of them is a pdata pointer. So for those of you who are not familiar with the format of type names in Windows, those are in uppercase, and when you have a P at the beginning, it means it's a pointer. So pdata of type p struct1, which means pointer on a type struct1, on a variable of type struct1. This pointer is probed. So probe is the equivalent of validating a pointer. So it's like, I can't remember the name of the Linux kernel function for that. It's not copy in user, but something similar, like access OK or something. So basically, whenever you pass a pointer from userland to kernelland, you have to validate it before you can dereference it. So that's what the probe and read macro does. So you validate that pointer, and then you take the data from that pointer. So cur data dot field 1, field 2, field 3, and you do some arithmetic, but you never validate the value of the field. So the result of the multiplication can be 0. So the count can be 0. Here you have the variable count in third parameter of underscore set data that is 0. So it gets continued. Third parameter is 0 count. And under the same condition that we control, with flag enabled. So all examples have been obfuscated a little bit so that we protect the guilty and everything. In the case where count is 0, you have this call user alloc pool. So user alloc pool is actually going to call the same function I mentioned earlier on. So whenever you do a user alloc pool of 0, it doesn't return null either. So if you do if temp equal null return R, it's not going to check any kind of zero size problem. So once you do this, you have the TMP array that is allocated with 0 byte. We've seen previously that it was in fact allocated with 16 bytes. And we do dangling pointer arithmetic. So here we consider zero-sized heap allocated pointer as dangling pointer because you don't really know where they point to if you do arithmetic on them. So save data arrow array becomes a dangling pointer in a kernel. However, when you copy memory with a count, since count is 0, so RTL copy memory is a function of the Windows kernel that is equivalent to memcopy. So if you just take it as memcopy, when you do memcopy of 0, nothing happens. So there is no vulnerability here. If you just look at the code of the syscall straight away, so you might be tempted to say, okay, so I just did zero size heap allocation, but I don't touch the memory after, so nothing happened. However, if you look at another syscall, you can see that the same pointer arrow array here is actually dereferenced. So if you analyze from a given syscall and you look at functions that are called, the call leader of that syscall, you can see that nothing happened. But if the pointer is stored to a kernel structure, in that case, save data, then it's stored in the kernel and it can be reused in another syscall, and then a memory corruption can happen. So under the same condition here, with a mask on flag enable, you can have indexing of the array. So in that particular case, it's not an escalation of privilege because you can just dereference the memory at an invalid location, so you cannot have code execution. So this is just a crash example, but nonetheless a true example of zero-size problem. Any question on the example? Yeah.
What version was this fixed in? What version of Windows did they?
Actually,
You don't have to answer.
this was fixed in the latest shipped version of Windows. So if you run Windows, a sufficiently recent version of Windows, you're protected of this.
Okay, thank you.
Oh, this is one of the reasons why we obfuscate the examples, because we don't want people to find back the vols. But if you know the Windows kernel a little bit, then it's not too hard either to find which version of Windows I'm talking about and which syscall I'm talking about. So just like put your hands in the dirt a little bit. So early conclusion from our example. When you have a zero allocation, it's not necessarily a problem. Sometimes it's perfectly safe. You do a zero size heap allocation, you don't touch the pointer, nothing happens, it's not a bug. When a real problem happens, it's not necessarily an escalation or elevation of privilege. It can be just a crash of the kernel like BSOD. And also, doing local checking, so say taking a syscall, analyzing the syscall, and going down, sometimes is not sufficient to detect the bugs, because we've seen that we have the syscall, and then we call a function, nothing happens, but if you take another syscall that uses the same data, then a true bug can happen. So you cannot just take one syscall, analyze it, and then do something else. Like you have to correlate the code review analysis of the multiple syscalls, or do other things that I'm going to present after. Okay, second example. So that was scenario 2 or 3. Here you have same kind of code pattern. You have L param, that is a pointer that is passed to the kernel from userland. So you validate the pointer, so you can see p setting. So all of this again was renamed, so there is no such structure p setting in the Windows kernel, but something similar. You take p setting, the L param parameter, you assign it to p setting, then you validate the address of a field reachable from p setting. So you know that you can read properly at p setting arrow data length. However, you don't validate the value that you read. So if you don't validate the value and you do +1, then you can have an integer overflow and then count becomes 0. So you do zero allocation. Again, you do RTL copy mem with 0 byte, nothing happens, but the PLS structure that was allocated is passed downward. Second parameter of underscore new internal function. Here, the parameter gets renamed to L-param, so we track L-param. And you can see that L-param becomes PSTR, and then PSTR is dereferenced. So we just allocated a zero-size heap pointer, and then we dereference the length field, but we don't know what is the offset of the length field in the structure. So it might certainly be after the safe offset. So CBalloc basically the value of CBalloc is unknown. You don't know what the value of CBalloc is, and then you allocate unknown size buffer, and then of course you copy memory with an unknown size, and what nothing could go wrong here, right? And indeed, once you start to have a zero-size heap allocation, then if you start to touch the memory, bad things can happen. You should check this very early in the code. So it's very rare to need a zero allocation. Sometimes you actually need to do malloc 0, realloc, and if you have a loop, so you want to start with a 0 chunk and get the chunk bigger as you go. But it's extremely rare. I've seen 1 or 2 cases in millions of lines of code. So in my opinion, zero heap allocation should be forbidden. However, for backward compatibility, this is still a supported behavior in most operating systems, as we saw. So here again, and this time is an exploitable bug because you write to the zero size heap chunk, and of course this triggers a heap overflow. You actually write twice because you do memcopy and then you put the terminal byte. So you have the possibility to write a byte beyond the bound of the buffer. Is this example clear, or does it need any more explanation? Clear? Okay. Okay. So we're done with the first two examples. I have a couple of additional examples at the end for near zero locations, but I want to switch to the automated analysis. So the technique we've been using the theorem prover Havoc is pretty nice, but I'm not going to stick to that. I'm going to present a couple of different automated techniques for automated static analysis or semi-automated static analysis. So I'm not going to focus on the particular tool we used, but have a more general approach to automated detection. So of course we need automated detection for, first of all, because whenever we do code review, we can always miss bugs. We have millions of lines of code to review. Sometimes we just like overview the code and we say, okay, it looks safe, but we don't have any higher guarantee. So we need actually tools to give us better guarantees. One of the techniques that you can use for automated vulnerability discovery is called data flow analysis. So data flow analysis is a very popular technique, especially in compilers, because it allows you to do optimizations, and you can detect also a good amount of bugs with just using data flow analysis. So what's good about data flow analysis is that it's rather fast. It converges rather fast. It's scalable. I mean, if you do it intra-procedurally, it means within the same function, it's rather scalable. If you do it inter-procedurally, it becomes harder, but it's still rather fast and scalable. It's conservative. Conservative means that it's going to compute an over-approximation of the result. So sometimes you're going to say that you have a bug, but you don't have a bug. So it's a false positive. So you don't miss bugs, but at least it goes fast. And what's bad about data flow analysis is that it's all hard-coded. So we have known data flow analysis algorithm is based on intermediate forms such as static single assignment, SSA, and everything. So you don't have a way to configure that. And sometimes also data flow analysis is too conservative. So if you have, say, a merge point, you do if-else, and then you merge. Sometimes you have to merge the information about the data flow analysis. So after you finish with the if-else, you don't know if you come from the if or from the else. So sometimes it's a problem if you want to have accuracy. Data dependence graph. So whenever you compute the diffuse chain, which means the dependencies between variables within a program, you can compute very easily this kind of graph. So here, the blue nodes are registers. It's an example taken from Spark binary analysis tool I wrote a couple of years ago. And you see the white node on the very top. You cannot read, but it doesn't matter. Just follow the colors. The white nodes are immediate values. The green nodes, in that case, are malloc, and the red nodes are free. So with data flow analysis, you can find lots of like easy events, such as use after free, or a malloc without a free, or even a free that was done on something that was not malloced before. So by just dumping the relations between variables, you can actually see if you have a malloc that doesn't lead to a free. So you just follow the dependencies between variables, and you see that the parameter of free doesn't come from a malloc, and this is a problem. So here, the green node doesn't lead to the red node, and you can say, oh, I have a missing free, I have a memory leak, or I have a free that was not, whose origin is not a green node, so I have a free that was not done on an allocated pointer. In case you have aliasing problem, which means you don't exactly realize that two variables actually points on the same variable, you can have false positive. So imagine here, this node, or this node, is aliasing the top node here. So actually you would have a complete graph here and no bugs at all. You have the malloc, you have the free, and then the malloc leads to free, so no bugs. But when you have aliasing problems, then you say, oh, those don't alias. So I have a bug, I have a malloc bug, I have free bug, but this is just because your alias analysis is too weak. So depending on what kind of data, like this is alias analysis, so it's rather more elaborated than data flow analysis itself. But this is the kind of problem you can have when you manipulate such graphs. Is the graph clear? It's no?
The letters are not so clear.
No, as I said, it's not so clear for me either. No, I don't see what's written in the letter here, but it's the name of the register and everything. So it doesn't matter really what's written in here, in there. It's the dependencies between the variables. So you like A, B, C, or whatever. So just what's important to understand is that whenever you have a green node, it means that it's the return value of a malloc. And when you have a red node, it's the parameter of a free. So normally, if everything goes right, the return value of malloc becomes the parameter of free at some point, right? But if you do the relation between variables, sometimes this doesn't happen. So, for example, in that case, the output of malloc isn't passed to a free because the two graphs are not linked, right? If this was linked to that, everything would be fine. But here, this is not the case. And as I said, maybe this is not a true bug, maybe it's a deficiency of the analyzer because actually you have an alias that you haven't computed properly. So here, this could alias to here, but your analyzer is too weak or it was just implemented quick and dirty and everything. And you lack analysis power or you lack analysis techniques to actually figure out the alias. So you say there is a bug, but it's a false positive. Second technique, so this was data flow analysis. So it's just one example of property you could figure out with just simple data flow analysis. You have lots of different data flow analysis techniques that I'm not going to develop right now. Second technique is called model checking. So model checking, I've seen some model checking experts in there. So model checking is a formal verification technique that is based on a state exploration. So you will represent the program as, say, an automata, and then you actually go from the entry point of the automata and you see if you can reach a state that is not satisfying the specification. So I'm going to be clear about that with an example on the next slide. So in order to specify properties, you have lots of different languages, say LTL, linear temporal logic. So that allows you, just an example here, G means like always. So you say always when you have the predicate alloc x, which means you call alloc an alloc function. When you have alloc x, then all the time x should be different than 0. So if this formula is not true, you're going to have a problem. Specification is not going to be properly implemented. Basically, you would detect a 0 location. So let's go for the example straight away. So imagine this very simple program. So you have a variable that is called pad, it's 0, and you have variable that is mode, it's an integer. So here we just check if mode is 32 or like M32 or M64. So imagine, it's a fictional example, I should say. This is not a true example, this is just for pedagogical purpose. If mode is not M32 or is not M64, then nothing happens to the pad variable, so it stays 0. And because the only constraint that you enforce on val is val bigger than 8, so val could be 0 too. So val times 2 plus pad could be 0. So when you write the corresponding automata for this program, you can see that you have a path in the automata that actually leads to those constraints. So you have the size that is between 0 and 16, and at the same time, you have allocation, and you see that size could be 0, given the constraint on the size. So this is a pretty poor man's example for model checking, and I'm really sorry for all the experts. But this is just like a matter of introducing this technique of model checking. So here, if you go from the top and then you follow what happened in the if or the else of M32, M64, you see that you can never reach a state where the constraint on the size allows a 0 location. So basically, if we go there, we know that no bug is going to happen. So as you can see, this is different from data flow analysis because here we represent the state space explicitly, unlike data flow analysis. So, any question about that?
So when you have mix, for example, you have a new, and then you have a free, or you have, for example, a malloc, and then you have a delete, and you have, this mix of between pure C and C++ allocation methods. Then you have trouble too if you don't track that. With this, should be pretty effective, right?
Well, I'm presenting multiple different techniques. So yeah, you can, this kind of the kind of property you describe is actually called type state properties. So type state properties are all the properties that can be represented by finite state automata. So as long as you can represent the property using a finite state automata, then model checking is very, very, very well suited for that. So malloc, malloc free, use after free, all those things, all those type state properties. Any more question about that? Nope. Okay. So what's good about model checking? It's a universal technique. So you actually give a formula. You don't hard code an algorithm. You give a formula. So I gave a very stupid formula, a very stupid and simple formula about in LTL, but you can actually write the formula in whatever language you want as soon as you have the proper translation to automata. So you have lots of existing tools. In Microsoft, we have Slam, for example. It was used on, it was very successful. It found really thousands of bugs in drivers. But it doesn't scale, right? Because you have to represent the state space explicitly. So as long as the program is big enough, then model checking doesn't finish, or you cannot even construct the automata. It depends, though. You have on-the-fly techniques and everything. But basically, for big programs, this technique doesn't work. And sorry for the big expert who do symbolic model checking and everything, but we can talk about this later too. Okay, theorem proving. So theorem proving is a third technique. So all those three techniques are rather independent. You can have intersection between them, but you can make them work independently. So in theorem proving, you construct a logical formula that represents the program. And this formula is called the verification condition. So what happens is that you put assertions in the program. So when I say assertion, so like assert, it doesn't have to be runtime, but assertions are useful in order to check the condition that you want to check. So say you can instrument the program statically to add assertions to be checked. And then if the verification condition imply the assertion at the location of the assertion, then all is fine because the program actually implies the specification. So it means everything is going to work properly. However, if the verification condition doesn't imply the assertion, then it means that there is a condition, there is a possibility in the program that the assertion is false. So I'm going to give an example, it's going to be very clear. let's take this example, exactly same example. Pad is 0, so this is a atomic formula where pad is 0. We call it F1. Then we have the formula F2, that is F1, a conjunction of F1 and size equal vals times 2, and val is smaller than 8, or smaller or equal to 8. So this is just derived from the syntax of a program, right? We continue. Here we enter the first condition. Pad is not 0 anymore. It becomes size of T32, and the size doesn't change, and the constraint on val doesn't change. We have the same here for the other case, where pad is equal to size of T64, and size is the same, has the same constraint, val has the same constraint. And then we have the merge point. So the merge point introduces disjunction, because we don't know anymore what the value of pad. Pad can be 0, because if we haven't entered at all the if or the else if, then pad could still be 0. So we have the same constraint on size, same constraint on val. However, pad can be 0, or it can be size of T32, or it can be size of T64. And here, the assertion that we want to check here, because we have an allocation, the assertion is that size should always be different than 0. So we actually check, does F5 implies all the time that size is different than 0? In that case, it doesn't, right? So we have what we call a precondition violation. So a precondition is a formula that you expect to be true at the beginning of the function. Also, you have a post condition that is a formula that is true at the end of the function when the function returns. So here, if F5 doesn't imply size is different than 0, then you have a precondition violation, and it gives you basically a location, a static analysis alert. So this is how works the tool that we use for detecting zero size heap allocation in the Windows kernel. It's called Havoc. Havoc is based on the Boogie theorem prover. So Boogie has a page on Codeplex, codeplex.com, that allows you to use it for your own project. It's even open source. So basically, Boogie has its own intermediate representation and does the construction of the verification condition for you. So it is very useful. Basically, what you would have to do if you want to use that is to do a translator from C to the Boogie intermediate representation, and then all the analysis happens on Boogie programs. So if you are curious about this project, you have this Microsoft research page. I've been a power user of Havoc, so it's developed in a different team than mine. However, I'm pretty familiar with internals now. It's a very handy tool, and I really highly recommend a view of that page. It works mostly for C programs. We just started to apply it for C++, but it's still work in progress, so we don't have any results about C++ programs yet. But it's really working very well for C programs. And it has a detailed user manual, so you can see all the formats of annotation. When I say annotation, this is a precondition, postcondition, or the assertions that you can write. So it has a detailed user manual for those annotations. So in the security team, we use that tool in order to find new bugs. Also, when we're aware of a bug, we try to find variation of that bug. So bugs in the same area that looks the same, so whenever we're aware of something that looks really fishy, we check the whole source code, the whole code base of Microsoft for the same kind of pattern so that we can uncover other vulnerabilities. Very quick picture of the tool. So you have the translator from C to Boogie, Boogie PL. PL stands for programming language. So Boogie has its own intermediate form I mentioned before. So Boogie PL is the intermediate form of Boogie. So we give this translator a C program to translate. We give it annotations. Also, we give it a memory model. So the memory model basically is a set of axioms that make explicit how act updates and read from the memory. So depending on the architecture, you might want to have different axioms for the memory model. Say you have ARM, the weak memory model, and everything. Those would be different axioms than say for Intel. And then once we have all of the information, we take the boogie program, which is a BPL file, we pass it to the boogie theorem prover that is going to construct the verification condition for us. And then the verification condition is actually checked by a constraint solver. So because in Microsoft, we use Z3, it's one of the best theorem prover in the best constraint solver out there. It has won like many contests and stuff. So with that one, it works pretty well. It was even really well. And either the property is verified or it's not verified. So in case it's not verified, we have a warning. And so in the compiler window, whenever we have finished to run the analyzer, we have a list of the warnings, and then we can review the warnings manually. So I wouldn't say this replaces code review entirely. This is more of a complement. Say when we have millions of lines of code, say 10 million lines of code to analyze, we cannot afford, because we have very few, we cannot afford doing code review on 10 million lines of code. So we use this kind of tool to do the filtering, and then we focus on the locations where the static analysis wasn't able to prove that everything was safe. Any question about that? 5 minutes. Okay, I'm almost finished. So just to give a couple of numbers, on the first test case, the theorem prover was able to filter out 19% of the location of the assertions. So in 19% of the case, the assertions could be proven either, or could be proven true. So we don't need to review 98% of the cases. After a couple of more tests, actually, this number is nearer 90% than 98%, but still, it filters out a huge amount of the attacks you face. So that allows us to focus on the weak points, or the point that the prover was not able to verify. For 1 million, order of magnitude, for 1 million line of code, we have about 100 warnings. So 100 warnings is something you can review in 2-3 days. So 2-3 days of work for 1 million lines of code is pretty cost effective, right? And we've done just like this very simple case, like just adding one for this one simple property where you just need to add one assertion. This requires the size different than 0 for xallocate pool API and for the related APIs. We uncovered multiple elevation of privilege in the Windows kernel. So it was about 10 bugs. And we found a couple of more by code review in other code bases, code bases that where our tools don't apply yet. But the zero location pattern is definitely present, and not just in the Windows kernel. So look around you, all those protocols where you have TLVs and stuff, where you receive from the network the size you're supposed to allocate. You know, I was mentioning mobile code area alone. Just look around. I don't have much time, so I'm probably just going to give a last example. If you're into Windows analysis, then you followed the whole SMB saga last year. One of the bugs of SMB was actually a zero location. So it was a very complex case because it involved 3 different components of the kernel. So you had the server driver, so I can say it's SMB now. And then the server driver forwards request to other drivers, say the file system driver, passing through a component of the kernel called the IO manager. So sometimes you do a request that, imagine you do a request from the server driver to the IO manager using an API called IO do request with a tainted size, so the size is potentially 0. And then you pass the 0 value to the IO manager, and it performs 0 location, and then the pointer is passed to another driver. So each of those drivers is potentially 1 million lines of code, right? So you don't want to analyze all of that. So what we do is that we put the preconditions, so the requires, or the assert, if you prefer, we put them on the interface function between modules. So with the domain-specific knowledge that we have from the kernel modules, or from whatever component of the code base you want to analyze, basically we avoid to enter multiple components by just putting the assertions on the interface function, so we don't just have to analyze the top-level components to find the bugs. Obviously, that would blow up if we have to analyze multiple millions of lines of code at once in multiple modules. Then it's going to take forever, and you're not even sure that you're going to find the bugs. So it's kind of practical just to put the assertions in the interface functions. Okay, I had a third part about DNS allocation, but I'm running out of time, so I'm just going to take questions now. And thank you for your attention.
Hi, thanks for the presentation. I have a question. Well, I really like you doing model checking and data flow analysis, all this stuff, but I don't really understand why why you shouldn't deal with the root cause. You know, why not just change the implementation of the heap and handle zero-size allocations like a special case instead of. Don't get me wrong, I really don't mind you guys patching bugs and stuff. I mean, that's a good thing probably, but why not just prevent people from, you know?
I understand. So, as I mentioned, actually, it's for compatibility with third-party code. So some people will actually do zero allocation on purpose, or you can have the pattern where you do malloc 0, and then you have a loop where you need to reallocate the buffer. So you do malloc 0 that is perfectly legitimate, and then you do realloc, 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 and then there is no bug, right? Because you should be allowed to do malloc 0, and then you do the reallocation of the buffer as the program gets executed, because you need more data, you need more space to put your input data. So if you just say, oh, a macro as a wrapper to malloc, if size equals 0, then return null, for example, then you're going to break lots of applications.
It's still perfectly possible. Of course, you have to change realloc as well, right? And instead of returning null, you have to return 1, 2, 3, 4, for example, and then check that in realloc as well, and in free and all these.
I agree with you. Like fundamentally, you should not allow this kind of stuff. But it's a huge engineering effort. Like it's not just like 10 lines of code to change, right? You really need to change lots of code to do that, and not just in the allocator, but also the application that use the allocator. So there is a trade-off between like safety of the code and keeping it working as it is, right? So the code base is super huge. So you cannot just expect to do a simple modification and everything. You know, we have people who do mitigations really 100% of their time, and they have to build Windows, and they have to build Windows to run like thousands of checks. And sometimes the modifications are really simple. You wouldn't expect them to break anything, but the simplest modification can actually break the code in 10 different ways. So it's not trivial to just do a simple modification like that. We would like that. We discussed it. We discussed inclusion in the security development lifecycle for zero locations, but it's not there yet. So we might actually decide to put it in there, but currently we still rely on like code review and automated detection, or semi-automated detection for this kind of vulnerability.
How does your memory modeling work for the comparison?
I didn't get it, sorry.
A few slides back, you were showing how you did this analysis.
Yeah.
Yeah, right there. Memory model, what are you doing with that?
So as I mentioned, the memory model actually is a set of axioms that describe how memory access work. So you'd say, for example, you'd say whenever you write into a variable, you'd expect that next time you read it, you'll have the value that you wrote, right? This would be an axiom described by the memory model.
So you're saying this thing in memory has to follow these rules, et cetera.
Exactly.
Okay.
So depending on the architecture, the axioms of the memory model are different. For example, on ARM, you might have to write twice the same value in a variable to make sure that next time you read it, you actually read the same value. So That's weird, but like
Thank
this
you.
is how it works.
I was just wondering, if you have all this architecture already, why only use it for zero malloc detection? I mean, you could use this for all sorts of weird things, like execution of code that shouldn't be executed, or buffer overflows. A number of things.
As I mentioned, the buffer overflow problem is very complex. So you can have a generic buffer overflow finder, but it's going to be really noisy. It's going to give you lots of false positives. So the idea of this talk is to have this very simple property that we know is difficult to handle for developers. So we limit ourselves to this particular pattern, and we uncover those bugs. So you could do the same, say, for particular size, say FFFF, say, because it's a boundary value, so boundary values are harder to handle for developers. But there is no such, actually, if you look at the literature, you'll see that lots of people have attempted automated buffer overflow detection, and lots of people do that, but most of the time it's super noisy. So you have hundreds, if not thousands, of false positives. So that's why you have to reduce the actual analysis you do in order to be able to review the warnings in a reasonable amount of time.
I'm not going to take the time, but I don't agree with you, because if this is a theorem prover, then that proves that there is no buffer overflow, or it proves that it is possible. So there is no false positive, and that's it. So the other possibility is that the way you transformed your code into the prover is noisy, and therefore the prover will give you a noisy output, but the prover is mathematically gives you a proof.
Okay,
but the question is, do you have the firepower, so the amount of clusters and CPUs to actually crunch through all that code, which I develop set solvers, so I know how difficult they are in terms of speed. So yeah, I understand, but I don't agree with you. In theory, in practice, of course, it's impossible because it's just too much time. But it would actually give you an answer, it's true or false, and that's it. It won't give you any noise at all.
So in theory, you can also put Paris in bottle, but we ain't with practice, right? So we want to do things that work. So indeed, in theory, theorem prover would be no noise at all. You can actually do. No, well, we can talk about it later. But in practice, you really have to reduce your analysis to what's actually tractable to review. You cannot. We don't have so much manpower on that. I mean. One of the disadvantages of theorem proving is that you need an expert to review the result, right? You cannot expect anyone to review the result of a theorem prover. So finding people that are able to review the result of a theorem prover is not so straightforward. So when you have millions of lines, dozens of millions of lines of code, you cannot expect to just fire a theorem prover on them and then find all the bugs, then you finish, your product is perfectly secure. The reality doesn't work like that. So we can talk later.
Why don't you do cleaner programming? So, for example, if you have some systems that have to work, maybe some embedded systems that control airplanes or stuff like that, then you would make some range checking, or even make a malloc with an assert, that so if you start to make a malloc with 0 size, it will assert, and then you get a trace record, and then you can trace it if you debug it, and you see, oh, the trace that it broke at address number so-and-so, and then you go to trace memory, and then you see that there was a 0 size malloc, and then you find what was the condition, and then you have to find that somebody was too stupid to make the code in the right manner. And so it would be better to fill such evil places with asserts that generates errors, and then you can trace this.
So if I understand correctly, this is a dynamic approach to detection, right?
Yes, and on runtime. So every time you write software, you have to test it in the system, and you get test vectors, and then you have to run it some months, and then you will see if it behaves correctly or if it does make some problems.
Yeah, well, in theory, you should put all the checks, and then the code would be perfectly secure.
You also in practice. So if you make some software that doesn't only control a word processor, but maybe controls some evil machines, then you have to do this.
You should absolutely do this. Of course, you should like check the values of the API so that no zero allocation can happen.
We're kind of running out of time, so we'll just take the last couple of questions.
I guess we're running out of time. How many minutes do we have? 5 minutes, okay.
My question is quite short. You mentioned Havoc being based on open source technology. I was wondering, is it itself released as open source?
Can you repeat, please?
You mentioned Havoc being based on open source technology, and I was wondering if it itself is released as open source. Or
Yes,
if it's
yes.
closed.
Boogie is open source. So you
great.
can actually take Boogie and apply it for yourself. However, the part that does the translation from C to Boogie is not open source. So it's tightly coupled to the Microsoft compiler, which is why it's not open source.
Yeah.
So you would say you want to reproduce this work for GCC, you would have to write the compile plugin that does the C to Boogie translation, and after you can use Boogie to do all the same analysis.
Okay, thanks.
In a few words, can you give some hints what the last chapter, near zero condition, is?
I could give an example, but it would be
Just
a little
few words.
Basically, sometimes you like. Let's see this slide. Sometimes you read the value from untrusted source. So say you have this function get value length that reads status arrow integer count. So you don't know the value of that, but when you do the malloc, you do this value plus 2. So the size holding variable is 0, but the size of the allocation is not 0. So if you check the precondition of the malloc function here, it's not going to trigger anything because the size is not 0. So require size different than 0 is true, right? However, you can have, say, an integer underflow on this variable. So I would have to explain it, and it's kind of a big example, so I don't have time to do that. But basically, in short, you can have an integer overflow or whatever integer condition, and it makes that the size holding variable is desynchronized with the actual allocated size. So this can be dangerous, and you cannot check it, you cannot find those with the simple precondition I described because require size different than 0 is always true. Am I answering your question? The slides are available, so feel free to look it up later and send me an email or like we can discuss it afterwards. I'll be pleased to answer your questions more in depth.
Can I ask a question? So I think all your examples contain just the unsigned integers. What about casting propagations and all the rules associated with comparison of signed, unsigned integers, short, long, and also floating point numbers? How do you model it in SMT? And
thank you. It's a very good question. So this tool supports bit vectors. So the constraint solver we based on, D3, has pretty good theory for bit vectors. So you can define a theory that talks about bit vectors, and so you would be able to find problems related to typecast and everything. So we've done that. However, in some cases, it's very, very difficult to do all automatically because you can have arithmetic on 31 bit size bit fields. And so if you do a cast from 32 bits to 31 bits, then you would actually have to track the fact that the bit field is just 1 bit less. And so you can have an integer condition on the bit field. So tracking that like on the whole kernel is sometimes hard. So it happens to us that we have some condition that says, oh, well, first of all, we run the analysis assuming that everything is 32 bits. And then we say, oh, okay, now we just put the option in the theorem prover to say that, okay, now we differentiate the 16-bit and the 32 bits, and then we just see the difference between the warnings. So that allows us to focus on those examples, on those warnings where just adding this new axiom give us a couple of additional warnings. So yes, the tool is able to differentiate those cases. However, it's more time consuming to do it because bit vector theory takes more time.
I'm sorry, so apparently we are running out of time for the next talk. So I think we should thank Julianne for patiently answering all the questions, and if there are any more, please take it away from the hall. Yeah.
Thank you.